So we are starting our very last section of general chemistry, right? Kind of sad. But any situation where we're transferring energy, these thermodynamic principles are applied. And it's kind of, I think it's kind of interesting. And for example, if is there energy in the ocean? In other words, could I take this energy out and do some work? Like, what I'm thinking of is heat, right? Because if I suck the heat out of the ocean, right, couldn't I use it to, right? Because then it would just turn into ice or something, right? Which might be kind of good for global warming. But the point is suck the heat out of the ocean, right? And then make it to run ships and stuff, right? Now, I don't know if we can do this. It's an engineering problem, fork out billions of dollars. But does it sound like it's okay? Because is there energy in the ocean? Right? Right? Why not? Because you have to suck that heat out to freeze it if you put it in the freezer or something, right? Now, and with money, Gates and Google have all this money, but they're not going to put a penny to this idea. Why? Because of this chapter. Physically, there's just laws of nature in the universe we live in. Some things are just bloody impossible. It won't work. Why not? It sounds awesome, right? Have a ship going in the ocean, and all it does is just kick out ice cubes, right? Just sucking out the heat. It won't work, according to what this is all about, okay? And we'll kind of, if you remind me at the end, I can explain why it won't work better. But these principles of thermodynamics cover photosynthesis, refrigerators, everything that's going on in your body, engines. Any place where there's energy transfer, this stuff works. For example, I'm going to need some help. Jose, I need some help. Okay. This is an IR thermometer. All right, let's see if, close your eyes, I don't want to shoot you in the eyeball. All right, it's 38 degrees Celsius. You biology majors, I guess that's normal, right, in Celsius? Okay, so you hold this, and what I want you to do is put it on there, see what the temperature is on that while I heat it up. What does it say? 26. All right, we need it hotter. So keep it going on there. This should work. We're going to find out. Try not to burn, Jose. You can keep it high because it's a laser. So all you got to do is just shine the laser. See the little dot on there? There it is. See that? That way it won't burn you. You got it on there? Yeah. There it is. All right. Just read the temperature out loud here so people can see what it's doing here.
48, 49, 50, 49, 64, 74, 85.
All right, it's getting pretty hot, right? Okay. So that's good. Everyone agree it's hot? So it's hot. Come on, dude. Am I doing the wrong? Maybe I'm going the wrong way. It's going the wrong way. They call this a Stirling engine. And it's supposed to, I forget which way it's built to go. It's built to go in one direction or the other. So what it's going to do, it's going to use the heat that's coming off of that hot block and move that piston. Oh, shoot. What's the temperature on top?
27.
27. Well, the demo's not working so good. Well, it's kind of going. Well, I should have played with it before we started, because this is the new demo. Anyway.
Right here.
Yeah. But the point is that, well, maybe I get it to work and I'll show you next time, right? But what it's going to do is it's going to use the heat to move that piston up and down and turn the wheel. They build these like they might have a huge magnifying glass with, and it shines it on the hot reservoir part. And this is thermodynamic terms, sorry, but it shines it on the hot reservoir part. The piston moves up and down, as the heat's transferred from the hot reservoir to the cold reservoir and things move. So you can get little turbines, get little electricity out of this just by huge magnifying glasses shining light on a hot metal plate, and they can get electricity out of it. So anyway, that's energy transfer. It's all governed by thermodynamics. Here's some tables that we'll get into. The first law of thermodynamics states that what? You can never get something for nothing. Work output can never be greater than the work input. Okay, all nice and dandy there, but what does it mean in a practical sense? This is a picture from the Smithsonian Museum in Washington, D.C. I don't know if I'd want to live in Washington, D.C., but it is an awesome place to go. All the things you can see, and all the coolest museums in the planet are totally free, the Smithsonian museums. So it's awesome. Anyway, this is a picture of a perpetual motion machine. And so it's a static picture, so you can't really tell. But a guy spent a lot of time and energy on this and having it perfectly weighted and everything. And this thing just continually spins around and around and around. Right? So, but having, knowing that this is impossible, it's kind of odd. I mean, how can that even be working? According to this first law, you can never get something for nothing. The work output can never be greater than the work input. According to the first law, the perpetual motion machines are what? Impossible, right? They're supposed to be impossible. Well, you got to look close at the little Smithsonian apparatus that's going on, or look really close at this picture right here. There's a cord. It's plugged into the wall. So it's just, I don't know why they even have it. It's really confusing. But maybe at small print they've got this all discussed. So you can't get something for nothing. Here's our mathematical equation that describes this first law of thermodynamics. Delta U is Q plus W. Now, I don't know how long ago you read this, Anessa, but do you remember what some of these terms meant? Ooh, change in internal energy. Well, can't write that fast. Okay, so change in internal energy, right? Okay, what was, before we keep going there, change. What's the mathematical symbol for change? Delta. That's that delta. That's what that triangle is. So when you read this, you can say delta U, or you can do what Anessa said, change in internal energy. So big capital U is the symbol for this internal energy. What are the units, Steph, for energy? Like distance could be centimeters or miles or something. What's energy? Anybody know? Joules, right? Now, our English system, we don't like to use joules. We like to use what's on the back of a Snickers bar, which is calories. Same thing. There's so many calories in a joule. You can convert one to the other. But joule is the unit of energy. That's a standard metric unit. This capital J, it's abbreviated. Okay. Mia, did you hear what Anessa was right? She named what Q was. It's other than H. Heat. Okay. So heat and little W, Alyssa. The only hint I can give you is that it starts with W. Work. Okay, so change in internal energy has to be heat plus work. That's the first law of thermodynamics. What are the units of delta U again, everybody? Joules. So that means Q and W also have to have units of joules, because joules plus joules equals joules. So everything has to have units of joules for this thing to work. Internal energy, what is it? It's all of the energy. I mean, what's kind of interesting, I think, is if you, like in this room, it's kind of stuffy and feels kind of hot in here, right? The gas molecules have all these different forms of energy. First off, they're flying around. That's one form of energy. Well, they're rotating. That's another form of energy. They're vibrating. That's another form of energy. So if you take all these different, they have nuclear energy. They have electrons are attracted to the nucleus. There's all these different forms of energy, right? We have energy that comes out of an electric socket. We have electrical energy. We have chemical energy. We have gasoline, potential energy. Right? All these different forms of energy, that's delta U, all of them. So you first, to talk about this sort of thing in thermodynamics, they want you to identify the system first. The system is Cameron. He's the system. So all the different forms of energy that he has in his body would be delta U. Well, how could you change it? There's only two ways, heat or work, okay, to change that internal energy Cameron system. Okay. The second law of thermodynamics. Rocks fall, hot frying pans cool down, iron rusts, tires punctured, high pressure shoots out. I mean, I could keep going on, but I don't know if I would get this across. Kenneth, what do all these things seem to have in common? Yeah, physical change. They're all, what I'm trying to get across is they're all natural, right? But the book doesn't want to use the word natural, right? You take a pencil and I let go of it, it drops. That's natural. Well, you're not supposed to use the word natural. You're supposed to use the word, starts with an S, Andromeda. What word are you supposed to use? S? Anybody know? Spontaneous. They are all spontaneous. They're all spontaneous. Iron rusts. So when they say, when a thermodynamicist says spontaneous, do they mean fast? No. It just means it's going to happen. It's going to happen before the universe ends. It's going to happen. Okay. So they are all spontaneous. Now here's the tough one, I think. And energy is blank. Energy is, well, increasing would be like, if I just let go of this pencil, it goes up. Or if you, it'd be unnatural, it would be increasing. Right? Because energy is supposed to get dispersed. It spreads out. Right? You take this hunk of chalk, right? Some machine pressed it into this nice fine shape. Well, you set up your little camera and you set this out in the forest or something, right? I don't know, someplace where it's not going to get disturbed. And you just watch it for years and years and years and years, and pretty soon it's just going to crumble, right? So energy is dispersed. It's spread out, but they like the word dispersed, so that's the word of choice. So energy is dispersed. It's spread out. Your textbook describes the second law with something like this. For any blank process, the blank must always increase. For any blank process, Audrey, the blank must always increase. This is how the book describes the second law. Any spontaneous process, you're halfway there. Now you got the hard one. It's the new word for the day, entropy. The entropy must always increase. The entropy, for any spontaneous process, the entropy must always increase. Okay. That, in essence, is what's wrong with the ice cube issue, with the boat in the ocean sucking up the heat and then spitting out ice cubes. It's not a natural process. You can't naturally get energy out of this. It's very unnatural. You're going to have to put energy into it to get it to work. Because think about it. You've got this energy dispersed all over the place in the ocean, right? Well, now you're supposed to take a portion of it. You're sucking out that heat. You're isolating the energy and sucking it out. You're doing the opposite. What we're really good at is blowing stuff up, right? Disperse that energy. Well, control those explosions in an internal combustion engine or something. But we're good at blowing stuff up, controlled explosions. So that's natural. That's why I guess that's why we got good at it. So a closer look at entropy. This ice melt in a warm room. Yeah, right? Energy gets dispersed. All right? Energy gets dispersed. You had this object that was nice and tight and small, it gets spread out. Energy gets spread out. Will the cold water molecules give energy to the warm? Oh, here's a natural thing. Do cold water molecules give energy to warm air molecules, or do warm air molecules give energy to cold water molecules? How does that work? Warm to cold, yeah. Isn't it hot in here? Talking about all this heat and stuff, it's making it worse. Does this thing turn on? Mia, how come you didn't turn this on? I know, you like the heat. All right. Maybe I can turn this one on, too. You guys are going to fall asleep in here. I'm already falling asleep. Okay. This conceptual stuff, it's pretty easy to fall asleep, I think. Entropy. Entropy is S. Delta S would be change in entropy. Is a measure of how spread out the blank is in a system. What would you guess there, Andrea? Good guess, but not quite. Heat is too specific. Internal energy, because the answer is really energy, right? How spread out the energy is. But that's not, there's all these different forms of energy. There's heat, there's electrical energy, there's potential energy, there's kinetic energy, there's all these different forms of energy. So it's the best way to give your answer is internal energy, because it composes all the different forms of energy. Enthalpy is a form of energy. Okay. Third law of thermodynamics. Jose, a crystal with no imperfections at 0 Kelvin has an entropy of they just gave it an arbitrary number. 0. They had to give it an arbitrary number because look how important this. Oh, we don't have the equation yet. Here it is. It's down here. We're going to use this because since this entropy is so tied to natural processes, we need a mathematical number for it. And it's kind of like measuring my height. You got to start from somewhere. And then usually you start from the bottom of people's feet or something, right? Or start from the floor. If you're going to measure everyone's height in this room, you start from the floor. Same way with entropy. If we're going to start and make nice tables of this stuff, we have to assign something. And then we'll make all our measurements with respect to that in the lab. They'll handle all that. And make all these nice big tables so we don't have to go do it all. So that's their baseline. And then they just called it the third law of thermodynamics. Kind of odd way to get a law, but that's how it is. Free energy and predicting spontaneity. Now we're getting into, hey, that boat won't float, or that, right? It's not going to make that boat go kicking out ice cubes. I think we've seen these variables before, Megan. What's delta G? Well, let's start with one that you know. Do you know any of these? Change in enthalpy. Now this is for brownie points, man. I will take a look right now at your grades and pick your lowest quiz score and replace it with a 25. Max it out if you can answer this question.
Together as a group, collectively, or individually?
If you know the answer, you have to raise your hand. Don't blurt it out. What is enthalpy? What is enthalpy? All right. If you want to make a guess, you got to raise your hand. All right. So we'll start with we'll start in the back. All right. We always start in the front, Megan. Okay, Kenneth, what's your guess?
Oh, I didn't have one. I set my hand like this.
Final minus initial.
Yeah, I'm not going to give away easy points. my gosh, you got it! Did you Google it? Heat transferred under constant pressure conditions. You Googled it, didn't you? That's good enough. We'll give you one. All right. Heat transferred under constant pressure conditions. It really doesn't matter too much to us because we're just going to get these numbers from what? A table. So if you know Cameron's definition or not, it really doesn't matter. Okay, we're going to get the stuff from a table. Change in enthalpy. T, everybody is... Yeah, delta S is change in entropy. But what's T? Temperature. And you got to watch your units on the temperature. Just make sure they cancel with the units that they give you for delta S. It's always going to be Kelvin, just to give you a heads up. Connor, how do you get temperatures into Kelvin? Celsius plus 273. Celsius plus 273. Okay. When blank is, this is the big one, because the homework, Enrique, is always going to say, hey, is this reaction spontaneous or not? And this is how you answer the question. It's with this blank right here. When blank is less than 0, the process will be spontaneous. And we're almost always talking about chemical reactions like rust. And we're going to look up, we're going to use tables to get numbers for all these. Oh, we didn't name them all. There's one left to name. Enrique, what's the name of delta G? Starts with the G. Gibbs. Gibbs free energy. Okay, now we've got them all named. We have them all named. So Anessa, when blank, you've got one of those up there in that equation. When delta G, when Gibbs free energy is less than 0, the process will be spontaneous. So right there's a good chunk of your homework. You're going to get delta G numbers, and if it's less than 0, it's spontaneous. More or less than 0, even a bigger negative number, more spontaneous. Different degrees of spontaneity. How do we get these numerical values for these variables to predict spontaneity of a chemical process? We got to get numbers for delta S, get numbers for T, get numbers for delta H, and then calculate this guy, see what that number is, and then if it's negative, it's spontaneous. Steph, how do we get those numbers? I changed it about 10 minutes before class. You can't even read these things. Charts, right? And no one brought their books, so that's why I scanned them. Okay. Charts. You know what's kind of silly? And the homework is going to have you do this. So just be ready to be a little perturbed and a little frustrated. The book is going to make you get this, because delta G is what you're after, right? To determine whether there's something spontaneous. Imagining charts. Do you see an easy way and a hard way to get numbers for delta G? Right? Do you see what I'm getting at? You can use charts to get delta H, use charts to get delta S, do the math and get delta G. But why not just use a what chart in the first place? A delta G chart. And the book is going to have you go both ways. It's silly, but that's, I don't know why they do that. Okay. How do you get these numbers? This is going back. We did this with delta H. It was called Hess's law. Using these charts, delta H for a reaction. Do you remember how we did it? We added up all the delta H's for the products, and then we added up all the delta H's for the reactants, and we subtracted the two. Products minus reactants. And that's what we did. So that's what you have to do for all these. That's how you get all of them. That's why they give you the charts. All those chemicals are in there that you can't read. Okay. A reaction is more likely to use, oh, here's a good one. Looking at this equation, let's see if you can figure this out. A reaction is more likely to be spontaneous if it is exothermic or endothermic. Just stop there. Mia, which one? A reaction is more likely to be spontaneous if it is exo. Why? You're right. Yeah, heat's given off, but that mathematically, that delta H number is negative, and you want delta G to be negative for it to be spontaneous, right? Because delta G equals delta H minus T delta S. So you want it to be exothermic. So you want, if you want something to be spontaneous, odds are it's going to be an exothermic reaction. Doesn't have to be though. Alyssa, we've got, you could be taken over by this part. The change in entropy is look at the equation, minus T delta S. Positive, right? Because then you'd have a positive times a negative. That would make it negative. So you want to keep that positive. So far you want there to be a lot of heat spread out, a lot of heat given off. The energy gets dispersed. Makes a lot of sense because there's so much heat produced. Okay. And the reaction occurs at a Andromeda, a high or a low temperature. How would you get the biggest negative delta G number there? A high temp. Because T is going to be in what units? Kelvin. Can you ever have a negative Kelvin? No. What's the lowest Kelvin you can have, Enrique? 0. Right. Okay. Simply by looking at a reaction, how can you tell if the change in entropy will be positive or negative for that reaction? This is a tough question. Simply by looking at a reaction, how can you tell if the change in entropy will be positive or negative? I think we should illustrate that answer with this question. There's a hint there. The only way you can tell is by looking at gas molecules. If you want energy to be dispersed, would you want the reaction to produce a lot of gas molecules or to produce few gas molecules? A lot, right? Because you want the energy to be dispersed as much as possible. So what you do is you look and see the change in gas molecules. So in this reaction, should delta S be positive, negative? Which one should it be? Kendall, you've been getting off easy this whole time. How many gas molecules are there on the product side?
4. Oh no. 2.
2. Good. There's 2 gas molecules over here. How many, Kendall, on the reactant side? There are 4. So should entropy be increasing or decreasing? Decreasing. So you expect delta S to be a positive or negative number? You said delta S should be decreasing. Negative, right? Final minus initial. Final is smaller than initial, so you should get a negative number. Okay, so let's try this. So here's the table. And again, you don't have it, so let me zoom it up for you here. You have the reaction, though. So as you would expect, we're expecting it to decrease. Let's see if it does. So let me zoom it up so you can calculate this. Okay. Can you read it yet? Still can't read it? I don't know. How big can I get this? I can't get it much bigger. You can read that. Just have Megan yell out the answers. Now, how are you supposed to get delta S for a reaction again? How are you going to get a number for this? products minus reactants, right? Make sure it's the right table first, right? Because there's a lot of different tables. So you want delta S for that reaction, so you have to find a delta S table. And they don't even say delta S, they just say entropies, right? They just say entropies. So see if you can figure it out. Look it up for the products, and then subtract it out for the reactants. I don't even know if they should all be in there somewhere. See, maybe we can circle them. C2H4 gas. Oh, here's C2H4 gas. That's a 219.2. Oh, yes, and multiply by the stoichiometric coefficients. Right. So C2H4 gas is 219.2. Oxygen gas, but you have 3 of them. Here's oxygen gas, 205. Yeah, and don't forget, like Megan said, to multiply by the stoichiometric coefficients. The products, we've got carbon dioxide. Here's carbon dioxide. Carbon dioxide is at 213.7. And we need water, but it needs to be liquid, not water gas. That's a big deal. Where is it? There it is. It's under oxygen. 188.7. Oh. Oh, thank you. Thank you, Anessa. 69.95, exactly. Water, liquid, thank you. So products minus reactants. See if you get an answer for this.
What did you say water was?
Water, liquid is 69.95. And don't forget to do what Megan said. She said multiply by the stoichiometric coefficients. Does anybody get an answer? Negative 266.9 is what Megan got. Anybody else get an answer? You got the same thing? Yeah, so that's got to be it. Negative 266.9, because 3 people got it. All right, now you don't want to lose points because of units, though. Use the table. The table will tell you the units. You have to have really good eyes to see it. Joules over moles Kelvin, right? Copy them from the table. Joules over moles Kelvin. Yep. So do products minus reactants. So 2 times CO2 plus 2 times H2Os minus C2H4 and 3 oxygens. So product, add them all up for the products, add them out for the reactants, and subtract those 2 quantities. So we're good? This homework, you'd love this, right? For each of the following reactions, state whether the reaction is spontaneous, non-spontaneous, or is easily reversible. How are you supposed to answer this? Look at the delta G. So what would you say for the very first one? Non-spontaneous? Cameron, what would you say for the first one? Delta G is a huge positive or negative number. Huge positive. Spontaneous was negative, right? So this, Anessa was right. This is non-spontaneous. This is going to take eons to form, if at all. You're going to have to put a lot of energy in to get that thing to go. It could be a highly endothermic reaction, maybe. But anyway, overall, it's very non-spontaneous. What do you think this easily reversible thing means? Jose, what do you think this means? That's because that's one of our options. Reaction ends up going either way. You end up with delta G close to 0. Exactly. So that would probably be which choice? The E. Yeah. Easily reversible would be this one. So D? Anybody, what'd you say D probably is? Non-spontaneous. Okay, so you got the idea how to do these? Or you want to practice some more? How do we want? Mia, you want to practice some more?
No, I meant like, you asked if we understood it, so I was like,
yeah, okay. But this isn't that bad, right? So we can hand out the exams. Just do products minus reactants, right? So make sure you use the right table. When they say calculate delta H0, use a delta H table. Calculate delta G0, use a delta G0 table. Okay? And interpret the signs. So positive delta H means, what word do you attach to positive delta H? That's delta G. Positive delta H, positive change in enthalpy, started with an E. Endothermic. Negative delta H, exothermic. Positive delta G, huge positive delta G, non-spontaneous. Huge negative delta G, spontaneous. Delta G close to 0, easily reversible. Very good. So you're not so bad.